Now, so far we discussed about the introductory part, then we saw some of the examples about why we need a Lagrangian formulation, but still we haven't answered to the question. I mean, the question that was been left unanswered last time was the following. What's the constraint equation? So, is there any further classification of the constraints? Well, yes, there is. The answer to this question. Let me state it. Just a second. Alright. So, classification is consider n particles. So r vector be the distance, and the I here signifies that it can be 1, 2 till capital N. Alright, please note the capital over here. So say if I have a function f which depends upon r vector to r vector n, r1 to rn, like we have just used this. So if a function that depends upon this r vector I and particularly and explicitly on time, it is an explicit time dependence. I mean, such type of equation are called as holonomic constraints. Holonomic constraints. Such type of constraints are called as holonomic constraint. So if a constraint is not of this form, I mean if a constraint is not of this form, we say it is a non-holonomic constraint. So let me write down. Okay, so this is a non-holonomic constraint. In this, if a constraint is of the form, if in this form, we call it as a holonomic constraint. The holonomic constraint is further divided into two subcategories. One is the renormous. One that depends explicitly on time, explicit time dependence, and other which do not depend explicitly on time, or say there is no t dependence at all. This subcategory, the constraint which explicitly depend on time, which has an explicit time dependency, is called as the renormous constraint. And this constraint which does not depend explicitly on time, or there is no t dependency, we call it as the Celerormous constraint. Celerormous. I know the names are a little funny over here, but that's the traditional names. So let me write it. So what I can do is I can construct a differential equation. So let me write it. This is a function which depends on r vector 1, r vector n, and it has an explicit independence, and it is equal to 0. With this, I can construct a differential equation. Now this involves partial differential equation as well as the and in higher dimensional case it also involves the gradient. So my this okay I cannot write every differential equation like each differential for r1 r2 and so on. So rather than to reduce to my notations, I'll use the concept of gradient. It means the same, and I here denotes that I is equal to 1 to n, and it represents each a gradient for each particular corresponding term, and this will be multiplied by r after I. Similarly, I can create a differential equation of t dependency. Thus we have delta t del t over here, we will have dt over here, and this is equal to 0 as seen from here. What I do is I say this term is my A and this term is my B. So I will have dRi plus B dt is equal to 0. So now you see we have a non-holonomic constraint which also have similar form along the holonomic constraint. We are going to use this, okay? Since we don't have a wide range of lecture, I do have the doubts of using this on a large scale, but this is what we are going to in generally be used. All right. So if you this particular form of constraint is, it's worth noting, this particular form of constraint is called as the Pfaffian form. Pfaffian form. Let me say so with retrospect to this equation, let me say something about the Celer-Nobis and the Riemann equation. So what happened in Celer-Nobis? So if a vector, these are vectors, I'm sorry. This is a vector quantity because it involves the gradient. So if a vector I are independent of P and correspondingly B is equal to 0, we say the equation is Celer-Nobis as seen from the Pfaffian form. Secondly, the Riemann. What happens in Riemann? Riemann contain explicit T dependence. If this is not the case, if this is not the case, we have Riemann condition. Alright. So also you can note this is just for extra, even this is extra. So if B is equal to 0, it corresponds to a condition called catastatic. Static means equilibrium. And if B is not equal to 0, you can just see the B is not equal to 0, there is going to be a dt term, and d by dft, there is going to be a change in respect to time, there is going to be a catastatic condition. So this is all about the constraints so far. So also I want to emphasize one thing. The non-holonomic constraint cannot be eliminated in any general method. You need to keep this in mind. This is very important. Alright. So what happens in case of holonomic? See, as we can see, they are categorized into two categories, which are holonomic and non-holonomic constraints. So holonomic constraint is the one that may be expressed in the form of an equation relating to the coordinates of the system and time. Exactly what we saw. Right? The general form is what we saw. Right? Now, in such equations, I denotes the ith constraint because we said I runs from 1 to n. Right? So it should be noted that all variables may not enter in the equation of constraint. This is very important. All should be noted that all variables may not enter in the equation of constraints. A non-holonomic constraint cannot be expressed in this type. So that's what we just said 3 minutes ago. So it may be in the form of an inequality, or like for case the equation of constraint. This is going to serve as a very important example. X square plus y square plus z square is equal to a square, right? So the equation of constraint in the case of a particle moving on or outside of the surface of a sphere. This is just a circle, but I'm trying to imagine. I'm just encouraging you to try to imagine this as a sphere in a three-dimensional space. The equation of motion in the case of a particle moving on or outside of the surface of a sphere of radius a, of course, it's going to have the other altitude and longitudinal terms. So we will have this kind of inequality conditions, and such inequality can be a non-holonomic constraint. So one of the things that you should note this, because we are going to use what I'm going to say. This is let me write it as very important so that it will just be fixed in your mind. It's very important. So if there are k equations of constraints, so if k equations of constraints, the number of degrees of freedom, remember, the number of degrees of freedom is what we express as DOF in classical mechanics, or in any case in physics, is reduced to 3n minus k. Alright, this is an equation. So if there are k equation of constraints, the number of degrees of freedom is reduced to 3n minus k. Hence, instead of 3n coordinates xi, yi and zi, where I, this is very important to specify every time, where I, capital N, we assign 3n minus k independent variables. So let me summarize this. If there are k equations of constraints, the number of degrees of freedom is reduced to 3n minus k. So the 3n coordinate system such as xi, yi, zi, where I runs from 1 to capital N, we assign 3n minus a k independent variables. So these are denoted by, say, q1, q2, q3, and goes to q3n minus k to describe the system. Alright, now such variables are denoted by such variables are denoted by just qi, where we can say I runs from 1 to 1 to 3n minus k. 3n minus k. So these variables okay, so let me summarize again so that it keeps it in mind, because this is going to be the base of the Lagrangian approach that we are going to take. If there are k equations of constraints, the number of degrees of freedom is reduced to 3n minus k. The 3n is given by xi, yi, zi, where I runs from 1 to capital N. We assign 3n minus k independent variables q1, q3n to describe the system, such as qi, and we describe this system, this q1, q2, q3 dot q3 n minus k by a single variable qi where I runs from 1 to 3n minus k. These variables, see, a set of independent coordinate system is set. Alright, a set of independent, see, this is very important, a set of independent variables of q1, q2 to q3n, proper set is called as a proper set of generalized coordinate. It should be noted that the constraints on the system are the consequence of the forces. Alright. Let me emphasize on that, what I just told. It should be noted that the constraints on a system are the consequence of the forces exerted on the system by constraining mechanism. Alright, we just saw the constraining mechanism. Now, this may not generally be known, hence it is necessary to eliminate the forces constraint. This is achieved by Lagrangian formulation. Alright, this is what is achieved. What are the achievement of Lagrangian formulation? This is one of the achievement of the Lagrangian formulation by introducing a proper set of generalized coordinate. Let me tell it. Let me repeat it once again. It should be noted that the constraints on the system are the consequence of the forces exerted on the system and the constraining mechanism. It is easy. That there is a constraint. There is constraints. See, the constraint on a system. See, there is a system and you have constraint. And the constraint are the consequence of the forces exerted on the system. Alright, it is due to the consequence of the forces that are exerted on the system. And the mechanism, I mean, what causes the mechanism may generally not be known, right? I just apply the force and there are constraints on the system. I don't know what is the mechanism. I don't know the mechanism that caused the constraint. Alright. So it becomes necessary to eliminate this kind of constraint that are caused by force. Alright. So this is achieved by Lagrangian formulation by introducing the concept of generalized coordinates. The choice of the generalized coordinates, it helps us to incorporate the constraints. This is possible only when the this is possible only, I'm sorry for my handwriting too, only when the system is under holonomic constraint. Now you see why I said holonomic constraint is the most important constraint, and that is constraint. Alright, just take a look. As I said, non-holonomic constraint cannot be eliminated by the general method because each problem needs to be solved in different approach. Each body, there is no generalizations, so as to speak, for a non-holonomic constraint, because it can be inequality. It can be, as we see in the case, the constraints of a particle on a sphere which goes in and out of the surface. So in next lecture I will speak about what's called as the generalized coordinates, and from there we will take a uplift. But before describing the so-called generalized coordinate, I will describe what's called as the configuration system and the state space. Configuration system, state space, and then I'll introduce the generalized coordinate system as a consequence of this. So that it becomes necessary, you will see it becomes necessary to introduce what's called as the configuration space, and state space is just another space that I'm going